So in the last lecture we did a bunch of stuff on denumerable sets, and we found that they were sort of remarkably robust, or at least the property of being denumerable was quite robust in that it was preserved under unions, intersections and Cartesian products. And so it makes it difficult to conceive that there's actually going to be anything bigger than denumerable. And that's the topic of today's video, or of this video. And that's about uncountable sets. So sets that are bigger than denumerable. So, uncountable. So, as I said, if A and B are denumerable, we saw in the previous video that the union of A and B is denumerable, and the Cartesian product of A and B is denumerable. Now, with a little bit of induction, we can show that if we have a whole bunch of denumerable sets, then any finite union is denumerable, and any finite Cartesian product is denumerable. And you can push this a bit further if you need to, but it's not too hard to prove something like this from what we did in the previous video. And so we're left wondering if we can find anything that's actually bigger. And the result that we're going to prove is that indeed you can, and we'll prove, using a very classical argument due to Cantor called the diagonal argument, that the interval between 0 and 1 is uncountable, and so the set R, all real numbers, is also uncountable. So just to remind ourselves, this is all real numbers between 0 and 1. It's not the ordered pair 0, 1. Okay, so before we do that, because a chunk of this proof is going to rely on properties of decimal expansions of real numbers, we should use a couple of facts that we won't prove here, but that aren't actually too difficult to prove. So first of all, every rational number has a repeating decimal expansion. So a third, for example, is 0.333. Just the 3's keep recurring. 2 over 11 is 0.18181818, so the 1/8s keep repeating. And of course you get something a little bit different from this, where maybe it doesn't repeat initially, but then it settles down into a periodic pattern. Okay, so every rational number has this sort of repeating decimal expansion. Now that's not so important, except that some rationals actually have two expansions. So for example, a half we can write as 0.5 with then an infinite sequence of zeros afterwards, or we can write it as 0.49 with just lots of 9s coming afterwards. And if you think about this for a little bit and do a little bit of geometric series, you can convince yourselves that this is actually the same number, expansions of 1/2. Now this only happens in the situation where we expand rational numbers, where the reduced fraction a over b, that denominator b is a product of 2's and 5's. And this comes from the fact that we're doing decimal expansions, namely base 10. And so weird things happen, or odd cases can happen when denominators are products of 2's and 5's, because 10 is a product of 2 and 5. Now, in addition to this, we need the fact that every irrational number has a unique non-repeating expansion. And so from these facts, we see that every number has a unique expansion except these ones. And in these cases, let's just pick the ones that end in lots of zeros and ignore the expansion that ends in lots of 9's. And so in this way, we can always choose a unique representation of any number between 0 and 1 as its decimal expansion. Now, the fact that the result that we're going to prove is due to Cantor, or at least proved by, published by Cantor in 1891, and the argument is now known as Cantor's diagonal argument. And this argument is really incredibly slick and has actually found uses in different places as well. It's a really beautiful idea, and so it's really great that we can get to that in this course and do stuff with it. So the result that we're going to prove using this diagonal argument is that the open interval between 0 and 1, that is all real numbers between 0 and 1, is an uncountable set, and so is not in bijection with the natural numbers. Now the way that we prove this is by contradiction. So we're going to assume that it actually is countable and show that that then gives us a contradiction. So, well, let's assume that it is countable. As I said, we're going to do it by contradiction. So let's assume that it is a countable set. Now, it's clearly infinite. We can put in there, say, all the numbers 1 over n for any natural number n. So we can see that it's an infinite set. So it must be denumerable. Then, because it's denumerable, we have a bijection from n to the numbers in 0, 1. Now, because we have that bijection, we can use that bijection to construct a nice big list. We can list all the numbers in the interval 0, 1. Now, it's definitely all the numbers in that interval because this is a bijection, so it must be surjective. So every number in here has to be the image of some n here, and so must appear in our list, just like the stuff that we discussed when we did denumerable sets in the previous video. Now, again, if some numbers have two expansions, indeed every rational number where the denominator is a product of 2's and 5's, then let's choose the expansion that ends in all zeros, so we have a unique way of representing every number that lies in 0, 1. Now, every number between 0 and 1 must appear somewhere in this list because that we've assumed that's countable and so denumerable. So now let's make this big array of all the things, and it's going to be the diagonal of this array which is actually key to this whole argument. So we build all the expansions out into a big table. So say whatever 1 maps to, whatever 2 maps to, whatever 3 maps to. So this is the first number in that interval, second number, third number, fourth number. And then we start building the expansion of that number going across here. So you can see all of these things. Now these are just some examples of what we might have here. But the key here is that because the interval 0, 1, we've assumed it to be denumerable, we can build this list of everything. And we can write out the expansions for each of these numbers, at least in principle. Okay, we're not actually asking to do it in practice, but in principle we can do this. And so maybe 1 maps to 0.78, 2 maps to 0.2, and so forth. Now, the important thing to note here is this diagonal. That's going to make everything work. So let's denote the kth digit of fn as fnk. So, for example, the third digit of f2 is 8, and the fourth digit of f3 is 0, so forth. Now, the diagonal here is just d1, d2, d3, and in particular, let's take the nth digit of the diagonal to be the nth digit of whatever fn is. So we'll find the nth number in our list, and then the nth digit of that number. And so we can write down this diagonal. Now, from this diagonal, if I can do it here, we write it out here, we're going to build a new number. So from this diagonal, which we can construct in principle, because it's a denumerable set by assumption, because we're trying to reach a contradiction, we can create a new number, let's call it z. So I've written down the diagonal here, delta, and then I'm going to build a new number z here. Now we create this new number z so that every digit in z has to be different from the digit in delta. So whatever we pick here for z, the first digit of z has to be different from delta 1. Whatever we pick for the second digit has to be different from that. Whatever the third digit has to be different from that. So I'm going to use the following rule. Let's build the nth digit of this new number, so call that zn, to be 1 if dn isn't 1, and 2 if dn is 1. So that's why 7, put a 1. 1, put a 2. 2, put a 1. 6, put a 1. 1, put a 2. 4, put a 1. And we've chosen this so for every single natural number n, zn is not the same as that nth digit of the diagonal, and so zn is not the same as the nth digit of fn. Okay, so the nth digit of the nth number in our expansion. So there's a lot of diagonals happening in here. Now, this is the really cunning bit, and this is why Cantor is really evident. He's really, really smart guy, and this argument is so slick. So let's think about this number z. Well, because all the digits are 1 and 2s, we know it must be between 0.111 and 0.2222, and so it is between 0 and 1, and so it appears somewhere in this table. Z must be somewhere in this table because it satisfies these inequalities, and because this table includes all the numbers between 0 and 1 by construction. Now, let's try to work out where it is in the table. Well, if z is equal to fk, if it's the kth thing in our table, then all the digits must agree. So that is, the kth digit of z must be equal to fkk. Okay, that is, all the digits of z have to agree with all the digits in the expansion of fk. And so that includes the kth digit of z. But by construction here, fkk, which is the kth digit of the diagonal, has been specifically constructed so it's not the same as zk. So z cannot be equal to fk. So z isn't in the table. Because if it were in the table, it would have to disagree with the diagonal by the way we've constructed things, so it can't be. So z is not anywhere in our table. And that contradicts the fact, or our assumption rather, that f is a bijection. And consequently, the set 0, 1 cannot be countable. Because if it were countable, we could construct this bijection, so we could construct this table, we could construct the diagonal, and then we could construct z, and then we'd have to find z in the table. But we can't. So this interval is not countable. So, as a corollary to this, we get almost immediately that the set of all real numbers is uncountable. So, in particular, we can also show that these set of the interval 0, 1 actually is the same size as R. We can do that by explicit bijection. And we denote the cardinality of the reals by this number C, C for continuum. Now, the proof of this, well, we could use the fact that earlier we proved that if a set B is countable, then any subset is countable. So by the contrapositive of that statement, if the subset is uncountable, the superset must be uncountable. So this is a superset of this, so it must also be uncountable. Now, we can also, so that's what we just said there, since that's a subset of that and is uncountable, had better be uncountable. We can also show that these are equinumerous by constructing an explicit bijection. So here's one here. This takes the interval 0, 1 to the set of all reals. You can convince yourself that this certainly has that domain and range, and you can convince yourself it's a bijection. It's quite an easy little exercise. So it's not such a difficult thing to do. So this was really a very, very profound result when it was first proved, because it showed not only that, well, the reals are different from the natural numbers, but it showed that there was more than one sort of infinity. And this was really quite earth-shattering at the time in mathematics, that people's idea of what infinity was just plain wrong. And so it's a really unbelievably important result in mathematics to show you that there's more than one sort of infinity, and that people's naive idea of infinity is just the set that just keeps on going forever, that's not sufficient, that there's much, much more structure, that there's much more interesting things going on than there's just a set that goes on forever. Because the reals, and indeed the interval 0, 1, cannot be put in bijection with a set of natural numbers. It's a very different sort of infinity. And Cantor, who proved this, actually came under considerable criticism for his result, and it was really not accepted for quite some time, and it caused Cantor all sorts of difficulties, the fact that he proved this result or was investigating infinity. So I recommend that you go and search engine your way to Cantor and discussion of him and the results that he proved. So I'm going to stop there.